So the final kinematic concept we need before we develop the conservation equations is Reynolds transport theorem, and that's chapter 3.6 in Kundu. And before we dive into the general Reynolds theorem, we'll go and look at Leibniz's theorem first. And Leibniz's theorem tells us how to take the derivative of an integral of a function. So let's say we have a function f of x and t, and we integrate it from a boundary a to a boundary b. And the important point here is that a and b may also be changing in time. And so Leibniz's theorem states that the derivative of this integral is actually given by the integral of a to b df dt dx. So this is essentially the change of f in itself, and then you have to take into account the changes due to the boundaries changing. So you subtract f of a and t times dA dt, and you add f at bt times dB dt. And I'm not going to do out the whole calculation here. I just want to illustrate it quickly, graphically, and then I'll post a link to a YouTube video by somebody else who does that very clearly, how to get from the black to the green here. So graphically, I think it's fairly intuitive. If you have some function f of x and t, and after a short amount of time, this changes to f of x and t plus dt, which you can Taylor expand, and that's just f of x and t plus dt times df dt. And so now we consider our two limits here, a and b, and they will change over the time dt. They will change to, so this initial integral, so that's just the integral of a b f of x and t dx. And then this green integral here, that would be our integral a plus dA b plus dB f of x t plus dt dx. And the quantity that we're interested in is this quantity, and it's by the definition of a derivative, that's the blue component b plus dB a plus dA minus the red one divided by dt in the limit of dt going to 0. So what Leibniz's theorem states is that the change in our function is associated with three areas. It is essentially the area integral from a to b times df dt. So it's this area minus f times dA dt, which is this area. The blue one is area 1. That's associated with area 1. The green one is area 2. And then the gray one is area 3. And that is, you have to add this term here, because you're gaining this area. And you'll see there's two areas that are sort of not accounted for. We should also subtract this area, but we're not. And we should add this area here, but we're also not adding this area. And that's because these are second order small. This is, since this is roughly df, and this distance here is dB, and this distance here is dA, then you can see that these two areas are small, so we can ignore them in this first order approximation.